Okay, so in this chapter, we're going to learn about atoms and elements, um, what matter is made of, and what we understand by atoms. Um, Not only that, so we'll also learn about these elements in the periodic table. So there are 92 different elements in nature. Okay, and they're all basically you'll see in the periodic table. And there are also some man-made, the 20 synthetic elements that are man-made. And then we'll learn about what atom is made of. So atoms, so far we have learned it is indivisible, but here we'll see that atoms are made up of neutrons, protons, and electrons. And it is the number of protons, okay, in the atom that determines the nature of the atom, the kind of elements uh, that atom represents. So atoms are basically the, according to Dalton, is the smallest indivisible part of matter. Okay, but here in this chapter, we'll see that atoms are actually, uh, made up of other particles. And when you think of elements, we say that elements is substance that cannot be broken down into simpler substances. So that means it cannot be divided into simpler atoms. So when you break up the atoms, what you get are those things that made up of that make up the atoms. That is the protons, neutrons, and electrons. So the initial Dalton's atomic theory has three parts. Okay, each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. And atoms combine in simple whole number ratios to form compounds. Now, when you look at this, these are actually great when Dalton gave the atomic theory in 1808. But later on, as we learned more about atoms, we came to know that atoms are actually, we can destroy atoms, okay? And all elements, all the atoms in an element are not the same. So we'll learn about isotopes. And also atoms combine to give complex molecules. So all three of them are kind of not true anymore. Okay, but still, these are great thoughts at that time. So now coming to the what atoms are made of, the different parts of the atom. It was J.J. Thomson, who first discovered smaller and more fundamental particles, and he called them electrons. So he was working with the cathode ray tube, which is our modern, you can think of the CRT monitors, okay, a kind of similar stuff. And from there, he saw that there's negatively charged particles, that come from one of the electrodes. And by studying those particles that are coming out, he could prove that they're negatively charged, and they are very light. They're almost 1600 times lighter than an atom of hydrogen. And we almost consider them as massless. Okay. And they're present in many different kind of substances. And because it is coming from the atom, he said that this negative, because there's a negative, atom overall is neutral, there must be something positive inside to make it neutral. And he proposed what he called the Plum pudding model. And it looks something like this. There's a cloud of positive charge in which the electrons are kind of embedded in there. But he could not explain how the electrons could be stable in a cloud of positive charge. So it was kind of rejected as soon as it was given. So for a long time, scientists believe that there's a negative charge particles called electrons, and there must be something positive, but they had no idea, how the positive and negative charge are placed inside the atom. So it was Rutherford who did his famous gold leaf experiment. So at that time, another branch of physics was developing, which is called radioactivity. So radioactive substances are those that give out rays, and there are three kinds of rays, alpha, beta, and gamma. Of that, the alpha particle is basically made up, is you can think of the alpha particle as the helium. Helium is a element, okay, gas. So you can think of like a helium atom uh, carrying two positive charge. That means two electron less. Okay, so it was like a big cannonball compared to an atom. So he bombarded that particles onto a gold leaf. Now gold leaf, you can beat it into a very thin sheet of gold foil. Okay, so it's a gold leaf. Uh, so uh, so the idea was that if what Thomson is saying is correct, okay, like there's a carton of positive charge, then all these particles, alpha particles, are going to, kind of bounce back. Okay. Uh, but what he actually saw in this experiment is this is a photographic plate, okay, and alpha particles, when they strike the photographic plate, it gives a like a illumination, okay, like an exposure. So what he saw is that most of the particle basically penetrated through the gold foil. Okay, and only few, 1 in 10,000, bombarded back in sharp angles like this. Okay, as you can see, like bouncing back. So what he said is that because most of the particle pass through, then most of the particles must be, most of the atom must be empty, and there are only small regions within the atom which is very dense and carries a very high positive charge, so that it can deflect a big particle like the alpha particles, and alpha particles are also positive charge. Okay. And he did some calculations, and from there he said that most of the atom is empty, and only a small region, which is called nucleus, okay, which constitutes probably 1 in 10,000 in volume, okay, constitutes all the mass and all the positive charge of the atom. And the electrons are basically spread around this empty space. Okay, and this is what we call Rutherford's model of atom. So in the Rutherford's model of atom, we have the positive charge in the nucleus. Now, these positive charge carrying particles, we call them protons. Okay. Now, if you think that you are keeping all this positive charge, they're going to repel each other, right? So it is going to be very unstable. She also proposed the existence of a neutral particle, which would act like a glue, and he called them neutrons. And it was much later that he's actually his student. Okay, later on, in 1932, Chadwick discovered neutrons. So now this is the current, for now, this is our, uh, you know, model of the atom, where at the center of the atom we have the nucleus, which contains positive charges and neutral particles, so protons and neutrons, and the electrons are basically dispersed around the particle, around the empty space. But again, he could not, explain how the electrons would be stable in that empty space. But we have to wait another 10 years for another branch of physics to develop, which we call quantum mechanics. Okay, so and then we could understand much of the atoms, or how the electrons are positioned inside the atoms. But for now, we have three particles, okay, electron, protons, and neutrons. Based on that, uh, we can now look at atoms as constituting electron, protons, neutrons, where the electrons are dispersed around the nucleus, and the nucleus contains these protons, and neutrons. So there are equal number of protons and electron, so that the atom itself is neutral. And the identity of the atom, depends on the number of protons. So, and electrons, are equal in a neutral atom, but you can have charged atoms, which you call ions, where there can be electrons, more or less electrons from there. Okay, so electrons can be exchanged, but not the protons. So this is something that you have to know. Now, this masses and all those things you don't need to memorize, but you have to know that the proton is like have a mass unit of 1. What that means is that you are comparing with the smallest atom that we have, hydrogen. Okay, so it has almost the same mass that of a hydrogen atom. Okay, neutrons are also mass is 1, that is equal to, when I say 1, that's very relative amount. Okay, so when I say the proton is 1, the neutron is 1, so it's relative. Okay, the actual masses are on the left, so you don't need to memorize the actual masses. And the electrons are almost massless. As regard to the charge, a proton carries a +1 charge. Again, that is a very relative amount. Okay, the actual charge is something different. Okay, so or electrostatic unit, ESU. And the neutron is neutral, no charge, 0. And the electron has a -1 charge. Now, during that time, we had enough data, and because there was a lot of elements to remember, scientists, started using what we call the symbols. And the symbols has some logical, way of putting the symbols. Like you take the first letter. If the first letter is taken away, you take the, first and the second letter. And when you write 2 letters, the second letter is written in lowercase. So when you write, then these are called symbols for the elements. And when you write these symbols, this capital and lowercase, they have a meaning. So you cannot just write both uppercase, then it will mean that they're 2 different elements. Now, you might wonder that why lead is Pb. Now, many of these names are Latin names because people are accustomed at that time to using Latin names. These symbols come from the actual Latin names. So lead is Plum, Pb. Mercury is Hydragyrum, and the symbol is Hg. Iron is Fe, Phenum. Okay, silver is Argentum, tin is Stannum, and so on. Okay, so many of these symbols we'll see are Latin or Greek names. Now again, these also you need to memorize. Okay, so we have to memorize the first 30 elements, and then I'll point out some, okay, which are very common. We'll be using it for writing symbols. Okay, now in the exam, I'll be providing you with a periodic table. But even with the periodic table, you still need to memorize these symbols because it becomes easier for you to write formulas when you memorize them. Now, so when the scientists looked at all these elements, so there are 70 elements at the time. Now we have more, but even within the 70 elements, scientists could see some similarities among the elements as to their properties, their activity, and so on. But they could not exactly, put a finger and say this is the pattern. So there's a pattern. So it was Mendeleev, Russian scientist. Okay, he, he tried to put these elements in some order. Now, at that time, actually it was started by Dalton. So Dalton tried to compare the atoms of different elements using their how heavy they are compared to the lightest element that we have, which is hydrogen. He said, let's take hydrogen as 1 and compare and put numbers. How much heavier are other atoms with respect to hydrogen? And he called them atomic weights. Okay, so Mendeleev arranged the elements in the increasing order of atomic weights, and he saw a pattern. Now that we know about neutron, protons, which was not known during the time of Dalton or Mendeleev, we now know that it is the number of proton that determines the identity of the elements. So initially, Mendeleev said that the physical and chemical properties of elements are a periodic function of the atomic weight. Now we talk about, instead of atomic weight, we say atomic number, which is the number of protons. Okay. Now here we have these elements, arranged in increasing atomic numbers. That means the protons. So 1, 2, 3, 4, there are a number of protons, and they're color coded. And when you look at the color, you can see that the properties are kind of repeated. Okay. So if you look at neon, it is similar to helium. If you look at lithium, it is similar to sodium, and they have the same color here. Okay. Now, if you take this block starting from neon and put it, easier it would be if you look here, like lithium, beryllium, boron, carbon. This is one series, and if you take the elements after neon, that is sodium, Na, 11, 12, 13. If you place them just below, their properties are kind of very similar. Okay, they kind of fall within a column of families. And so the properties of lithium Li, okay, which is 3, and sodium Na, 11, potassium 19, they have similar properties. Now, if we extend this idea to the whole array of elements that we now have today, okay, we get our long form of periodic table. So this is a periodic table where you have these columns and the rows. Okay, the column are families of elements having similar properties. So that, which means that if I know one of the element, I can predict what the properties of other elements would be within the same column. So we call them, family of elements. Now, in this periodic table, things to note is these particle columns, these are called groups. And the horizontal rows, these are called period. Now, when you arrange it, the periodic table automatically divides the elements into metals and non-metals. So if you look at this zigzag line, all elements which are left to the zigzag line are non-metals. Now, what are non-metals and metals? So metals so we all understand what metals and non-metals is, but in chemistry we say metals are those that can lose electron. So they might have a metallic luster or may not. They may be solid or may not. Now all metals are actually solid, okay, except and have a metallic luster. There's one good example, mercury, which is a liquid. So now mercury is still a metal because, and you can see mercury here, Hg, number 80. Okay, so it is a metal. It is a metal because it can lose electron, but it's still a liquid. Okay, and if you look at the non-metals, non-metals can gain electrons. So that's the fundamental definition, difference between a metal and a non-metal. So if I ask you, where do you find the non-metals? They're in the upper right-hand corner of the periodic table, and all the metals are to the left of the zigzag line. And these particle columns are called the groups. So you have 1A, 2A, and then 3A, 4A, 5A, and so on. Okay, and the elements that are in the borderline of the metals and non-metals, they are called metalloids. So they have properties in between metals and non-metals. So they are good semiconductors. Okay, they are very good semiconductors used in the electronic industry, like silicon, germanium. We know silicon industry, right? And that is because they are good semiconductors. Okay, so if you look at this list of properties here, typical properties, metals. So they are good conductors of electricity, heat. They are malleable, ductile, lustrous. But the most important property when chemistry comes in is they can lose electrons, and that's why Mercury is a metal. Okay. Now, if you look at the non-metals, on the other hand, uh, there you get solid, liquid, gas, everything. Okay. Uh, so, you can think of nitrogen, oxygen, they are gases. Among the solids, you can have sulfur, phosphorus, liquid, bromine is a liquid. Okay. So you have all kind of, you know, states there. But the most important property for the non-metal is that they can gain electrons. Okay. So electrons are the one that can be transferred, not the protons. So these elements can tend to gain or lose electron depending on whether it's a metal or a non-metal. And metalloids, as I said, are kind of in between the metals and non-metals. Okay. Now, if you look at the periodic table, as I said, the particle columns are called group numbers, and elements in a group, they're very similar in their properties. So that kind of makes our life easier. So if I know the property of one element, we can predict the property of rest of the elements. Okay. And the horizontal rows are called the periods. Now you can also see that the periodic table is kind of has some blocks here. Okay. So the yellow blocks are called the main group. Okay. So you can basically join them together, and this yellow block, ignoring the blue here. The blue is called the tensor metals. Okay. So if you just join the yellow blocks, you can see it goes from metal all the way to non-metal. So there's a gradual change of property as you go from, say, lithium all the way to neon. Okay. But the middle group, which we'll understand later, kind of sits in between them. Uh, and they're all metals, very similar properties. We call them tensor elements. Okay. So they are called transition elements. Okay. This blue group here. And the yellow groups are called the main group. So when you think of the gradational properties, we talk about the main groups. Okay. And the tensor metals do not have much changes there. They're all metals, like a block of metals. There are 10 metals, okay, in a series. And we'll see why they suddenly appear there, okay? Not now, later, when you understand quantum mechanics. Okay, so the main group elements properties can generally be predicted based on the elements position. So easy to predict the main group elements. Okay, and we can see there's a gradual change from being metal to a non-metal. Okay, and the tensor elements tend to be less predictable because they're all similar. Okay, if you think of iron, copper, nickel, cobalt, zinc, they're all metals, kind of similar. Okay. But if you think of lithium, it's a highly reactive metal, and then you have chlorine, okay, in iron, which is highly reactive non-metal. Okay, and there's a change of properties as you go from left to right. So some of these, these are basically families, these vertical columns, because they behave similarly. And this family of elements have a name. And there are four that we should know. Group one is called the alkali metals because they all form very reactive alkalis, okay, bases. Alkaline earth metals are less reactive, and we use them as antacid, okay. And then group 7 is called the halogens, and group 8 earlier used to be called the inert gases because they are very inert, they would not react. Nowadays, we can react them, okay. So we do not call them inert anymore, we call them noble gases. And then there is this block of element below here. They actually fit into this white gap. Okay, but in order to make it look better and for us to understand, we take it out. And they are called the inner tension metals. Okay, they're the lanthanides and the actinide group. There are 14 elements in there. Okay. Now, for our purpose, okay, we need to memorize, these elements up to 36. Okay, 1 to 36, and then you need to memorize lead, bismuth, okay, um, silver, cadmium, indium. So all the way up to 36, and these are additional ones because we will be using them for our reactions. Platinum, gold, mercury. Okay, and here we have iodine, xenon. Okay, so these elements you need to memorize. Okay, palladium. So 36 plus these elements that I marked here. Antimony, tellurium. Okay, so you'll come across these elements. So uh, very often, and you need to know them and identify them. So you need to memorize them. But I'll be providing you with the periodic table. But even with the periodic table, you'll see that it will be most convenient if you know where they are to find out when you need them. Okay. Now in the actual periodic table, uh, you will see that there will be atomic weights and all those things done. So there are a lot of information carried in the periodic table. Okay, so here we are just showing the atomic number and the symbol, but you'll also have the atomic weights. So we'll use the atomic weights for different calculations. So you need to go and figure out. If I say what is the atomic weight of tin, SN, you should know that tin is SN and where to find it so that you can get the atomic weight from there, even though the table is in your hand. Okay. So it actually it needs some practice and you have to give some time to look around in the periodic table. So these are the elements that you should memorize. Okay.
Okay.
Now, as I said, atoms can gain or lose electrons. So when they gain or lose electrons, they become charged. So these charged particles or the charged atoms, we call them ions. The positive charge ions are called cations, and negative charge ions are called anions. Okay. Now, ions can attract one another. So the positive charge ions come together with the negative charge ions to form a compound. And we'll see those kind of compounds. These are called ionic compounds. Like our sodium chloride, the table salt that we use is the ionic compound. It is made up of sodium ion and the chloride ion. Okay. Now, the way to write the ions, and this is very important in chemistry that we follow the rules. Okay, you write the symbol, and then the ions go as a superscript on the top. Okay, 2 plus. So magnesium 2 plus. That means it is an ion of magnesium. Similarly, oxide ion O2 minus. Okay, so you cannot write it on the side. You have to write it as a superscript on the top. Okay, uh, because there are other things we use for the side and also for the bottom and left and right. So we use almost all parts, in chemistry, and we'll come across all of them gradually. But this is for the charge, the top, upper right hand corner. Now, if you look at the periodic table, you will see that if you look at the main group, so we are talking about the main group here. Tensile metals will not talk about much. Okay, so they are all metals, so they all form plus charge. But if you look at the main group, okay, uh, then you can see that the group number is equal to the charge for the metals. Like all group 1 forms plus 1, all group 2 forms plus 2, group 3 forms plus 3. And if you look at the non-metals, they are negatively charged. Now, you can imagine why. So when you are making a positive charge, that means you are taking away electrons. And now if you take away two electrons, you are taking that second electron against a already existing positive charge. So it is difficult. Third one is even more difficult. Fourth almost never happens. Okay, so uh, you know, atoms do not form plus fourth charge usually. Uh, so that and then as you move to the right, instead of losing electron, they tend to gain electron. So fluorine takes minus one electron, oxygen takes one electron, and so on. Now we'll see a pattern here. Okay, if you look at the metals, your charge is equal to group number, and if you look at the non-metals, is basically how far they are from group 8. Okay, so group 7 is 1, right? And group 6 is 2 distance apart. Group 5 is 3 distance apart. And so elements in group 5 will form -3, like nitrogen. Okay. Now, as I said, just like losing electron, gaining electron also becomes difficult because you have to push the electron in, okay, against the already existing negative charge. They're going to repel. And so after 3 negative, they do not want to form 4 negative. So if you look at group 4, okay, we haven't assigned any ions there, but we'll see later that there's tin and lead, okay, tin and lead that can form ions, okay. Uh, so tin and lead. So tin can form +2 and +4, lead can form +2 and +4 ions, but not, but they are within the metals already, okay. Okay, so now, so this is basically our periodic table. Now we'll look at the periodic table a little bit more closely in the later part of the chapter. Uh, Now coming back to original Dalton's, Rutherford's, uh, model, as I said, the number of protons determines the identity of the atom, and then neutrons are basically neutral. So you can have atoms that have the same same number of protons, but they can have varying number of neutrons. They're still the same atom. Like you can have hydrogen with no neutrons. Okay, that's our regular hydrogen, or most abundantly found hydrogen. And then there are hydrogens with one proton, okay, and one neutron. And the hydrogen, one proton and two neutrons. They are all hydrogen. All three of them are hydrogen, but the one that carries neutrons are heavier. We call them heavy hydrogen. Okay, so this kind of atoms that have the same number of protons but different number of neutrons, we call them isotopes. Okay, and these isotopes are naturally present in our uh, in our universe. So when you are collecting, let's say, a neon gas, you are basically collecting all kind of isotopes there. It's like if you're collecting apples, you have the large apple, you have small apple, right? So it's like that. So all are apples, but still one is larger than the other. Uh, so if you think of it, this is the collection of neons. So if you take 100 neons, out of that, 90.48% out of 100, okay, will carry this neon 20. That means it has 10 protons. All of them has 10 protons. All of them here has 10 protons because they're all neons. But this one has 10 neutron. Uh, this one has 11 neutron, and this one has 12 neutrons. So they're all neons. Now, just like the red apple and just like the apple, like large apple, small apple, they're all in this one basket. So when I am taking the mass and trying to take what is the mass of one neon atom, it's an average of all these large and small ones, and that is what you call the average atomic weight. Now we can also calculate this average. Okay, we'll look at the math. Okay, this is the only math we have here of calculation, and then we'll see how to say that there are 11 neutrons or 12 neutrons, and that is what we call the nuclear symbol. So this is the isotope symbol notation, also called the nuclear symbol. Okay, so we write it. There are three ways of writing. Now this is a more I would say a more complete way, where you have the symbol, and right here you have the atomic number. Atomic number means number of protons. Okay, and the mass number is neutron plus proton. So if you look at, so if I give you a symbol of neon like this, okay, which means there are 10 protons, and there are 10 protons and 10 neutrons. And this is a way of symbolizing that nucleus. Similarly, the next one is 11 neutrons and so on. Okay. Now the 10, when I say the proton number is 10, I really don't need to write it. Okay, because I can figure it out. Because all neons has 10 neutrons. We know that. So it's kind of redundant. So many times you will see it's written like 20 Ne. So you don't write the one at the bottom. Okay, the 10 is implied. It is there. Okay, and another way of writing this is you can just write it as Ne dash 20. The three ways of writing it. One is this one is this one, and third one is this one. And they all say the same thing. So what the kind of question that will ask you here, like I'll give you a symbol like this and ask you how many neutron, protons, and electrons are there. Let's say for this one, how many protons are there? 10 protons. Yeah, because you see the 10 here. Okay. So this is 10 protons. Now, if I ask you how many neutrons are there, 12 neutrons, because you subtract, you get the number of neutrons. Total is 22, right? 22 minus 10, that's great, Diana. Yeah, that is exactly what you do. 22 minus 10 is 12. Now, if I ask you how many electrons are there, now protons are positive charge, electrons are negative charge, and the atom is neutral. So there must be equal number of, uh, equal number of electrons. So the number of electron is 10. So for this, let's say I give you another example, sodium. Okay, and I say sodium, let's say 23. Now, I'm not going to tell you that sodium is 11 because you'll be provided with the periodic table, and you can go there and look. The sodium is 11. So number of proton is equal to 11. Okay, what is the number of neutron? So number of neutron is 12, right? 23 minus 11 is 12. Now what is the number of electron? 11. Electron is minus, right? So equal. So yeah, so they will be equal. In this case, they are equal. So this is 11 electrons. Now if I give you Na plus, that's an ion. That means one electron less. So, and I give you 23. Okay. So here the number of proton is equal to the same, right? But proton will not change. Proton is still 11. Neutron is 12. But the number of electrons is, because it's plus, is one electron less. Electron is negative charge. So number of electron is equal to 10. Now, if I give you another example, Cl minus. Cl minus, and let's say 35. Now, if you look in the period, now, why don't you look at the periodic table and tell me what is the number of proton? So go to the periodic table, which is,
I see it.
This one. And right here, you can see chlorine. Now, so that's why you need to, memorize the periodic table.
Yeah.
Even though you have the periodic table in your hand, it's easy to find. Okay, you have 17. Okay, so the number of proton is 17. So number of proton is 17, and the number of neutron would be 18, right?
Mm-hmm.
And then what is the number of electron then? Remember, it has a negative charge. So it will have one more than the proton, and there are 18 electrons. It's pretty, straightforward and simple. Just you have to be careful. Okay, you have to take care of the charge here, minus or plus, or is it neutral? So as I said, this is like a basket, right? Where you have all kinds of different size thing, and here we have three types. Okay, this is one type, this is the other type, three types. So now if I think of an apple, okay, think of three kinds of apples you have. Okay, so what do? You take the whole basket, right? You take the whole basket, take the total mass of the apple, and divide by the number of apples,
Yes.
right? So that's the average. So if I am working in a grocery store, that exactly I'll do. What is the average mass of apple? I'll put the basket on a. Now here, uh, so we are basically weighing. So we know if we have the mass of each of these, different size apples, like the three sizes here. So I'll multiply by the number.
Mm-hmm.
So here I'll multiply by one into uh, whatever I have, right? One into whatever the mass is given. I'll add them. Then this one I'll this is 9.25. Now this is a percent, means out of 100. So and multiply by whatever mass of these apples are. And similarly, I'll do 90.48 multiplied by the size of these apples, and then add all of them together, right? That is the mass of the total apples. And what is the total apple? My total apple is 100 because it's percent, right? The
Yeah.
total apple is 100. So I'll add them, and then uh, I'll divide this by 100, and that will give me the average atomic mass. Simple, glossary math. Okay. So that is exactly what we'll be doing here. So you basically take the fraction of the isotopes. If you multiply by the percent number, the percent means what? When I said 9% is 9 by 100. So this is called the fraction. So if you take the fraction, you don't need to multiply by 100 again. Okay. So the formula is fraction of the isotope. So the fraction means actual the percent given in fraction. So if it is 9% means 9 by 100. 10% means 10 by 100. So fraction multiplied by the mass of the isotope 1, fraction multiplied by the mass of isotope 2, fraction multiplied by mass of isotope 3, add them all together. And that's it. You are done. You don't need to, because it all adds up to 1. All these fractions add up to 1. Okay, so you don't need to divide by 100. So please don't divide anymore by 3 or anything. Okay. So that makes the math simple. So if you look at this simple question here, the atomic mass, so naturally occurring chlorine consists of 75.77% of chlorine 35. So the chlorine 35 is a name. His actual mass is 34.97. AMU is called atomic mass unit. So we really don't have the mass in grams, right? Uh, so we compare it with hydrogen. So when you compare hydrogen, we say atomic mass unit. It's a relative unit. Okay, so that's 34.97. Now the other variety of chlorine. So the chlorine gas is a mixture of two gases, actually, two isotopes. That is 24.23, and it has a mass 36.97 AMU. So if I want to calculate the average atomic mass, I'll multiply the fraction with the isotope mass. Okay, and for isotope 2, I'll do this and add them together, and this is my average atomic mass. Clear? And no matter if you have, three isotopes, you'll be 40. Now, oftentimes, I would not give you the last one. Like I would give you uh, 75.77% chlorine 35, and there's a mass of 34.97. And I will say that the rest is chlorine 37 with a mass of 36.97. So when I say rest, that means 100 minus this amount. Okay, 75.77. So even though for 24.23 is not given, you should be able to figure that out. In the three isotopes, the rest means you add the first two and subtract from 100 to get the rest.
Mm-hmm.
Okay. And do it systematically, write it nicely so that you do not get confused, so that the trouble, the math is straightforward. I know you can do it. Only thing is that what I find out is careless mistakes, or multiplication problem, or doing addition is a problem. And another big mistake that I see, that in a question like this, like there are two isotopes, after doing this addition, students will multiply by two, divide by two. No, don't do that. And another thing, remember that the average will be somewhere in between these two numbers, right? Just like a apple, right? So it cannot be even, something outside the range that we have. It will be in between the ranges of apple that I have when I take the average. And same for the isotopes. Okay. So if you see a number which is outside this range, then you can always go back and check because something is wrong. Okay. So that's a cross check you can always do. So here is another example. Okay. You have gallium has two naturally occurring isotopes, gallium 69 with the actual mass 68.9256. Okay. And the natural abundance is 60.11, uh, and the gallium 71 is 70.9247, and the natural abundance is 39.89. Now, if you add them up, it will always be 100. Okay, if it is percent. And the other thing is, if I don't give you the second one, you can always figure that out by subtracting from 100. Okay. So calculate the atomic mass of gallium. What I usually do, I am kind of, you know, I do not believe in myself when I'm doing math, because uh, I you can get into a lot of problems um, just from careless mistakes. So I write down. So gallium 69. Okay, this is the name. So I say isotope. So there can be more, right? So there can be many. Usually I won't give you more than three. Okay. So this is the isotope. And then I'll write percent. And then I'll write abundance. So this is a systematic way of doing it. So I'll look at the problem, fill up this chart, and then, atomic weight, the actual atomic mass that is given. The atomic mass, and I'll put a unit, mu. Always it carries a unit. Okay. Anything measured quantity will carry a unit. So, well, this is percent, 60, gallium 69. If you look around, it's 60.11. Okay, so I'll write 60.11. And the abundance is divided by 100, so 0.6011. Okay, and the atomic mass is 68.9256. Now, the second isotope is gallium 71. So that's the name. So gallium 71. Okay. And if you look around, so this is 70.9247. Okay, that's the actual atomic mass, and the abundance is 39.89. So 39.89.
39.8.
And so the abundance is 0.3989. And the actual atomic mass is 70.9247. Okay, next, what we need to do? We need to multiply, right? Okay, I need some space here. So I'll just cross it from here. Okay? The mu is actually here. So if I multiply, so what I multiply? I'm multiplying the abundance, and so this I'm multiplying. So let's do the multiplication and write the numbers and then add them up. Now, if you look at this is fourth significant figure. So because I'm multiplying a fourth significant figure. Okay, so this is fourth significant figure. So that means my answer is fourth significant figure for this one. So I put underline under 3. Now I'm multiplying the second one, 0.3989. 28.29 okay, 28.2918 or 19.
Mm-hmm.
19. Now this again, the underline comes here under 9. So when I add them up, so this is the limit of my number.
Mm.
Right?
Yes.
And the unit is AMU in both cases. Okay, so if you add up, what do you get?
69.72 AMU.
Okay, so 69.72. And you see, if you add up these, you get 1 and the 3 here, right? So if I look at the next number, it is basically 3. That means I truncate, right?
Yes.
So I would not. So my correct answer is 69.72. And that is the answer you will see we are getting. Okay, this many AMU. That's the average mass of all these isotopes when you take together. Okay, so see now again this is the abundance. Okay, we divide by 100 and then you multiply them. And when you're multiplying, remember this is the limit of the number, and we add them. We pick up to this much, so 69.72. So you have to do it. You can do it this way as long as you keep track, of the significant figures. So these two decimal places, 69.72. So this is the other math that you have to do in this chapter. Okay. So one is the calculation of neutron, proton, electrons, and another is this one, average atomic mass. Now these isotopes are useful things. Okay, some of them are radioactive. So what is radioactive? They give out rays. Okay, and these rays comes out from the nucleus. We say nuclear radiation. Okay. So we can use them for various purposes. Now these rays are actually harmful. So they do biological damages to our body. They trip the DNA or mutate our DNA and so on. So prolonged exposure can lead to cancer or genetic diseases. But they can also be put to useful purpose. Okay, like detection of thyroid, that your thyroid is working properly, can be detected by radioactive iodine. Okay, and also when you do chemical reactions, the different steps of the chemical reaction you can figure out by using isotopes. So they are that way very useful. Okay, so isotopes in the environment, so usually they are harmful, as I said, but we can still use some for good purposes, and some of them they have a half life. That means that is the time it takes for them to get halved.
Yeah, no
So the
problem.
beneficial uses, as I said, radioactive iodine is one of that. Then technetium 99 is often used to diagnose disease. Okay, so there are a lot of uses there, and also many cancer patients are treated with radiations, and those radiations come from like cobalt 60, okay, gamma radiations, because they can kill. So radiations can kill cells. So if you are careful enough and focus it exactly to the cancer cells, you can kill the cancer cells. Okay, and now you have to be careful that you don't damage your normal cells along the way. Okay, so this is the summary, okay, of all that we just did. So it's kind of nice summary. So the elements we can classify the elements from the periodic table into metals, non-metals, and metalloids. So you have the zigzag line. Okay, the right of the zigzag line, we say upper right hand corner, we have the non-metals, and everything to the left are non-metals. And at the border line, you know, along the zigzag line, we have the metalloids. So they have characters both like metals and non-metals. And then each of these has a chemical symbol that you have to memorize. Okay, the elements that are indicated. And the arrangement in the periodic table, when you look at it, we have the groups, we have the periods, and these groups, within the group, there are some groups that are names. Okay, like alkali metals, alkaline earth metals. There are 4 of them that you need to know. Okay, group 1 is the alkali metals, group 2 are the alkaline earth metals, group 7 are the halogens, and group 8 are the noble gases. Okay. And then there are trends in the periodic table, which is right here. Okay, now these elements consist of atoms. Okay, atoms in their subatomic particles like proton, electron, and neutrons. Okay, now protons, they determine the atomic number, and they basically indicate what that atom is. Okay, or the nucleus is. So proton doesn't change, number of proton doesn't change, but electrons can lose or gain, can be gained by the can be lost or gained by the atoms. So you can have ions like plus ion and minus ion. Plus ions are called cations, and minus ions are called anions. And the protons and neutrons together made up of the nucleus, and that is what we call the mass number, n plus p. And the neutrons, number of neutrons can vary, which give rise to isotopes. And the natural abundance of isotopes are variable for different elements. And when you try to get the average atomic mass, we're taking the average of all these isotopes. What we do is a weighted mean. We take the whole mass and divide by the total number. So we did some math, and there's the kind of questions that we get in the calculations of average atomic mass. Rutherford said the electrons are around the nucleus, but didn't specify how they can stay there. So later on, Niels Bohr, by the use of quantum mechanics, okay, figured out the energy levels. The electrons are in discrete energy levels, and he called them principal quantum number, n equal to 1, n equal to 2, n equal to 3. And each of these energy levels can contain a definite number of electrons, like 2, 8, 18. Okay, the outermost electrons are called the valence electrons, and they basically dictate the property. So elements in the same group have the same number of valence electrons, and the group number basically is equal to the number of valence electrons. Okay, so the group number basically tells you the number of valence electrons. Now comes the periodic trend. Okay, if you look at the periodic trend, so you have the atomic size, you have the ionization energy, and there's a metallic character. And important is the size. If you know size, you can basically predict all of them.